Hello everyone, welcome back to the new section of numerical method course, and in this section we will learn about numerical differentiation. In the last section we learned about numerical integration. Now we are going to see about the numerical differentiation. Already we have seen how the differential terms, that means each of the differential terms with respect to independent variables, can be represented numerically in lesson 4 using the central difference formula, backward difference formula, or forward difference formula. Those are the main formulas that are frequently used for representing a differential term and an equation in terms of numerical values. So those are the main differential equations or techniques, that means the forward, backward, and the central difference methods. So those are the main equations, but beyond those equations we have some certain cases like the partial differentiations or unequally distributed data. So for these cases we need to use some special techniques to handle those special situations. So in this lesson we are going to learn about these numerical differentiation techniques. So these were the formulas that we have learned in the lesson 4. So if you remember, these equations were of first derivative formula of forward divided difference, and these were the second derivatives, third derivatives, and fourth derivatives. So these are the main equations that we used for our purpose in lesson 4. So for example, in first derivative we have shown you two different equations. The first equation has an order of accuracy of first order of accuracy, and the second equation has an order of accuracy which is O of h square. Okay. Similarly, in the second derivative we have two equations. The first equation has an order of accuracy 1, and the second equation has higher order of accuracy to be 2. Similarly, we have third order of derivative and fourth order derivative. Next we have these backward difference formulas. These difference formulas are similar to the forward difference, but we use the present data and the previous data for calculating the derivatives. So similarly we have two equations for each of the derivatives: first order derivative, second order derivative, third and fourth. Okay, so the first equations have lower order of accuracy and the second equations have higher order of accuracy. So if you remember that the both forward and backward divided difference formulas had an order of accuracy, first order of accuracy, but if you remember that the central divided difference formula, these equations had an order of accuracy to be 2. That means central divided difference had an higher order of accuracy than the similar forward or backward difference formula. So if you have to choose between among the forward, backward, or central divided difference, so you should go for the central divided difference, because with the same effort we will get higher order of accuracy if we use the central divided difference formula rather than the forward or the backward one. Okay, so these equations we have already covered those equations in lesson 4. So if you want to see some examples using these equations, please go to that lesson and review the examples there. Okay, now we are going to see some amazing things. Actually, we have known that the Richardson extrapolation can be easily used in increasing your accuracy, and we have seen that this Richardson extrapolation was covered in numerical integration, and we have seen that Romberg integration was based upon this Richardson extrapolation. But the amazing thing is that this Richardson extrapolation technique can be easily extended to numerical differentiation. So you can apply the same theory, apply the same formulas for Richardson extrapolation actually. Okay, so the main theme was that if you have some preliminary results using the basic techniques, so you can easily manipulate those primary results to get a higher accuracy, to get a result with higher accuracy. So that's the main theme of Richardson extrapolation. So we are going to use the same formulas that we have used in the numerical integration section. Okay, so if you remember, that we have if we have two different step sizes like h1 and h2, and h2 is half of h1, then we can easily easily calculate the formula, this formula which is of which has an order of accuracy to be 4. Okay, so these two differential values, d of h2 and d of h1, these two differential values are our preliminary results, so they have an order of accuracy to be 2. But these equation, after using this equation, Richardson extrapolation equation, we will have an value which is d, and it has higher order of accuracy which is 4. Okay, similarly, if we have two different values of order of accuracy to be 4, then we can manipulate those two results to get a final result with an order of accuracy 6. Okay, so this is the equation that we used in numerical integration section. Similarly, we can use this equation for to get a value with an order of accuracy to be 8. So these are the formulas that we have already seen in the last section in numerical integration. So these formulas remained the same. Okay, but the difference is that in those formulas in integration we use the integration results, but here we will use the differential results. Okay, so these are the equations, Richardson extrapolation. So for better understanding of these equations, if you want to know about the proof, so please go to lesson 36. We have covered the proof there. Next, we will see how actually we can use these Richardson extrapolations to get to implement those formulas for Romberg differentiation. Actually, Romberg differentiation and Romberg integration both are same. So if you want to see an example using the Romberg differentiation, you can go through the example that we have covered in numerical integration section. Okay, so the technique is absolutely similar. So if you just want to have an extra overview of the Romberg differentiation, so go to that section. Okay, next we will see that how we can use the derivative techniques to actually apply for unequally spaced data. Okay, the unequally spaced data points have some limitations. Now we have seen about the forward difference formulas, backward difference formulas, and central difference formulas. These formulas can be applicable whenever we have uniformly distributed data. Okay, the step size is similar, the step size remains constant. For those cases we can actually apply these formulas. But what about the unequally spaced data? These data can appear in many experiments. If you do any experiment, you will see that some of the data points are not uniformly distributed in the space. As a result, you will have to do some you will have to use some special techniques to handle this kind of situation. Okay, so let's say you have a function given, you have some data points that follow a function or equation. In that case, what you can do, you can generate some new data points and actually gather some new data points using that function to represent the whole space and whole data space as uniformly distributed. So that is one way to uniformly distribute the data points which were originally unequally distributed. But for that purpose we need to know the function or equation. But what about the situation whenever we are not given the function or equation? In that case, we cannot generate new data points. Okay, so what we can do actually, that we cannot actually use the divided difference formulas that we have seen. Okay, we have to use some other techniques to handle such unequally distributed data which cannot be represented using any function or equation. So we are going to use the Lagrange interpolating polynomial. So in this lesson we are again encountering the Lagrange polynomial. We have already seen that Lagrange polynomial can be used for curve fitting, numerical integration, and now we are here which can be where we are using the Lagrange polynomial again for differential purpose. Okay, so we have already discussed that Lagrange polynomial is a general theory. Actually, we can use this Lagrange interpolating polynomial for any purpose. Whenever we need to fit a line or curve with some data points, then we will use the Lagrange polynomial. Okay, so let's say I am given 3 data points, 3 adjacent data points. For that purpose, we need to generate a Lagrange polynomial of second order. Since we have 3 data points, we can easily generate a second order polynomial. Okay, and that means a quadratic equation. So Lagrange interpolating polynomial of second order looks something like this. This is the second order polynomial, and how we get each of these terms is actually covered in the curve fitting section. So if you want to know how these different terms, there are 3 terms here, okay, 3 data points, and that's why we have 3 terms. So how these 3 terms can be represented, how these terms were calculated, you can go for an overview in section in the section of curve fitting actually. Okay, so what we can do, we can easily differentiate this Lagrange polynomial analytically. Okay, so Lagrange, if we analytically differentiate the formula of Lagrange polynomial of second order, we will get an equation something like this. So we are just differentiating with respect to x. Okay, although we are just using the analytical formulas, but yet this technique can be called a numerical method. Why? Because the polynomial that we have derived are using the numerical techniques, and that's why we are calling it the Lagrange polynomial for differential purpose, and we are using it in numerical methods. Okay, so here x is the value. Let's see, we have on the left hand side it is f prime of x. That means x is the independent variable. So x is the value where we are estimating the derivative. Okay, so Lagrange, there are some advantages of Lagrange differential formula. The first advantage is that you do not need the data points to be equally spaced for constructing a Lagrange differential formula. So see, we are constructing a second order Lagrange polynomial here, so it doesn't matter whether the data points are equally distributed or not, because Lagrange polynomial does not work like that. So if the data points are unequally distributed, the Lagrange polynomials can be similarly constructed. Okay, so we do not need the data points to be equally distributed. The second advantage is that the derivative, we can estimate the derivative at any point. Okay, at any point, we using the Lagrange differential formula, we can estimate the derivative, and we need just 3 data points for second order derivative. The last advantage is that the Lagrange polynomial provides you the same accuracy as does the central difference formula. We have already seen that the central difference formula has higher accuracy than the forward and backward difference formulas. So this Lagrange polynomial also gives you the same order of accuracy like the central difference formula. Okay, let's look at an example whenever you have the unequally spaced data. So how you can use this Lagrange polynomial formula. Let's say I have a temperature gradient. I want to calculate the heat flux of the soil air interface. Okay, this is the air, and this is z equal to 0, and downward we have the z axis. Okay, and it represents the depth of the soil. So at the air soil interface here, z equal to 0, then as you go downward, the value of z increases. Okay, we have 3 data points here. These are the data points, and these data points actually correspond to the temperature. Okay, on the x-axis, on the horizontal axis we have the temperature, and on the vertical axis we have the depth inside the soil. Okay, so the heat flux at the soil air interface, at the interface of the soil and air, the heat flux can be represented using the Fourier's law. The Fourier's law is represented something like this. This is the equation where we can calculate, using which we can calculate the heat flux. The heat flux is denoted by Q. Q is, its unit is watt per meter square, and K is called the coefficient of thermal diffusivity in the soil, which has a value of 3.5 times 10 to the power minus 7 meters square per second. R is called the soil density. Soil density, which is approximately 1800 kilogram per meter cube. It is given, it is a parameter that is given, and C is called the soil specific heat, which is approximately 840 joule per kg. So each of these terms, Q, K, C, R, these terms appear inside this equation. Okay, so we have to calculate the heat flux at Z equal to 0. Z equal to 0 correspond to the air soil interface. Okay, to calculate the air soil interface heat flux, we need to calculate this differential term. Okay, remember, I am sorry, there is a small mistake here. The soil density, we are denoting it with R. It should be rho. Okay, it should be rho. Rho is the soil density, it's not R. So we have to calculate the heat flux, we need to know the differential term, this differential term of temperature with respect to Z at the Z equal to 0 value. Okay, to calculate this dt by dz, that means the differential of temperature with respect to the depth of the soil, we have 3 data points given here. Okay, on the figure on the right hand side, you see we have 3 data points. Okay, with these 3 data points, we need to calculate this differential term. Okay, let's see how we can do that. Since these data points are unequally distributed, to calculate this differential term, we need to use the Lagrange polynomial. Okay. So that's why we are going to use the Lagrange differential polynomial. We have already seen how we can derive this formula from the original Lagrange polynomial equation. So in this equation, we are going to substitute the original values of x and y variables, of x and function variables. Here function variables means the temperature variables. Okay, at different x variables, we are going to use a different function variable. So on the figure, we have used a z variable, so that's why here actually z is equal to x. So at different x variable or z variable, we are going to find out the function value or the temperature value. Okay, so that's the main thing we are going to do. So we can easily calculate f prime of x. So we need to calculate the temperature at z equal to 0. Z equal to 0, that means we need to use x equal to 0 here. Okay, so that's how we can calculate the differential term, that means differential of temperature with respect to the depth of the soil. So that turns out to be minus 1.333 degree per centimeter. Okay, so now we can easily calculate the heat flux Q at the air soil interface Z equal to 0. We are going to use the value of temperature gradient in the main Fourier's formula. Okay, all other parameters are given in the question, so we can easily substitute those parameters and we will get a value of 17.56 watt per meter square. So that's the result. So in this example, we have just learned about how we can use the Lagrange polynomial for unequally distributed data points. Now let's extend our concept of differentiation for partial derivatives. So if you remember what is the definition of partial derivative, let's say we have a function f which depends on 2 different independent variables, let's say x and y, and if we want to differentiate the value, if we differentiate the function, we can differentiate it with respect to either x or y. So we can calculate either delta f by delta x or delta f by delta y. So if you just differentiate with respect to x, you need to keep the value y constant. Okay, so for a specific value of y, we can calculate the differential value with respect to x. Okay, so this is the central difference formula. If you just visualize the function, it represents the central difference formula. Okay, it is actually the central difference formula. So similarly, we can differentiate the function with respect to y, and in that case the x variable should remain constant, and in that case we will get the central difference formula whenever we are just differentiating the function with respect to y. So This is the partial derivatives concept actually. So you see there is no new method, no new formula actually. You just need to keep the other constant, which is not the independent variable here, a constant. Okay, now we see that's how can we use the partial derivative concept for mixed partial derivatives. Let's say we have this mixed partial derivative delta square f, which is differentiated with respect to x and y. So we can easily separate these two differential terms into two different terms. Let's say we first differentiate the function with respect to x, and then we differentiate it with respect to y. Okay, so if we just differentiate the function with respect to x first, the equation should look like this. See, that's the equation. Look at this, the differentiation of function with respect to x. So these two equations are similar actually. Now we need to differentiate this whole term with respect to y. Since in the denominator we have no variable y, so we do not need to differentiate it. We need to differentiate the two terms in the numerator. So now we need to differentiate it with respect to y, and we are going to do that with two separate terms. Okay, now we can easily represent these two different functions here on the numerator. We can easily represent these two different functions with respect to y, differentiation with respect to y, with this format of equation. So how will it look like? The whole equation looks something like this. So in the first case, in the numerator, the first term can be easily derived from the first derivative with respect to y. Here we are just differentiating the function with respect to y, and that function is a variable of x plus delta x comma y. Since we are just differentiating with respect to y, that means these x terms will remain constant. That's why we see x plus delta x remaining constant, and since we are differentiating with respect to y, we are going to replace the y variable with y plus delta y and y minus delta y divided by 2 delta y. So this is the central difference formula with respect to y. Okay, similarly we can just differentiate the second term in the similar way. We are just keeping the x minus delta x term constant. Let's see here, the x minus delta x term are remaining constant, and we are just using the central difference formula, and that's why we are using y plus delta y, y and y minus delta y. So that's the final equation that is being used for mixed partial derivatives. So we have seen the simple single partial derivatives, that means with respect to x or with respect to y. In that case the equation looks similar to the central difference or forward difference or backward difference formulas, but in case of mixed partial derivatives the equation is a slightly more tedious actually. Okay, so now let's see an example that if I have some uncertainty inside my data space, what will happen actually. Let's say we have some experimentally available data points here. On the x-axis we have time, and on the y-axis we have some value, let's say y value. Okay, so these are the data points that we actually gained, and if we just differentiate these data points, these tabular data points, we will get a simple straight line. Okay, that's the differential. If we just differentiate these data points, we will get this curve. Now let's say I just introduce a small perturbation inside my data points. Let's say this middle data point has some uncertainty. That means if we are just doing an experimental task, these data point can vary a little bit along the y-axis. Let's say this data point has raised by a certain amount along the y-axis. What will happen if we just differentiate it? Let's say if we just differentiate it, the whole curve will look like this. That means we have just perturbed the system with a small disturbance, and as a result the error is amplified. Okay, so seeing these, visualizing these curves, we can easily deduce that the differentiation actually amplifies the error, and the reverse task, that means the integration, smoothens the errors. Okay, so that's the differentiation. The difference between differentiation and integration. Integration actually reduces the error, but differentiation amplifies the error. Okay, So in this lesson we have learned about the numerical differentiation, about the Richardson extrapolation and Romberg differentiation. We have known that the Romberg differentiation actually is similar to the Romberg integration. So the procedure is actually the same. Only in this case we are just using the differential values, not the integration values. And we have seen for unequally spaced data points we are going to use the Lagrange differential formula. You can actually use the Newton differential formulas, but in most of the cases we actually go for the Lagrange differentiation formula. Okay, we have seen how a physical problem can be solved using Lagrange differential formula, where the data points are unequally distributed among the space. Okay, and we have also seen how the single derivatives or ordinary derivatives can be extended to partial derivatives. We have seen the mixed partial derivatives have a tedious formulas, but we can easily calculate those formulas. Okay, and we have seen that if we have some uncertainty inside our data points, and differentiation actually amplifies those errors, but integration reduces those errors. So this lesson, actually this is the only lesson that we are covering under this section, numerical differentiation. So if you just want to go for some examples, you can go to lesson 4. There we have some similar examples using the forward, backward and central difference formulas. Okay, so in the next lesson we will start our new section which is about ordinary differential equation. So till then, thank you so much.